This is a drag and drop software, which it has a library, the green file that you see here called master library. So if you click on it, you go to the library of PSCAD. There are a lot of components here. In this project, we're using just very simple ones. We use the source, the three-phase source. We use Pi model for our lines. This is the Pi model, and we also use passive components in terms of constant load. So these are kind of the samples of the library. If you click on the arrow, you go to the entire library. So the way it works, let's say I want a capacitor, you just click on it, then right click, and then copy, and then click on the file that you have here, and then paste, and then you have your capacitor. So I've already built this, and I included these ones. These are buses or nodes, so you can give it a name, a base kilovolt. This is a multimeter. It can measure voltage, current, power, active and reactive, even frequency and angle, which we don't have any use for it. But you have a lot of settings here. The important ones are base MVA, so the number that it measures for you is going to be in these base numbers. So if the meter reads 1, it means 1 MVA in this case. Same goes for voltage and then the current. And this is, if it's three phase, then it's going to be line to line. So there are descriptions there. You can also go to signal name and then name any signal that you want, and it will record it, and then you can plot it later. And you can have animations on it, which means when you run the actual file, these numbers start to change in real time. These are your transformers. Instead of 1-3 transformer, I used 3 one-phase transformer, so because the configurations were different. But then I also put multimeter here. Now, it's the same multimeter here, but when you put it in a single phase, PSCAD automatically knows that this is a single phase. So you don't have 2 for 3 phase and single phase multimeter. These are for branching or splitting a 3 phase one line diagram to 3 actual phases. So this is a 3 phase system, then these branches out to 3 single phase, and then you get it back. The important part is these blue dots, so they represent phase A, and these should be on the same side. So if I put it the other way around, I actually create a short circuit, and it's not going to work. This is a Pi model. Now, in 4300, they talk about Pi model, and we're going to talk about it a little bit in chapter 6. But basically, it's modeling a distribution line with R, L, and then 2 capacitances at the beginning of the line. So it's like a pi, Greg pi, so that's why we call it Pi model. And then there are different ways to write the impedance here. You can change it. The way that I have written it is in ohms. So you have to go to this in ohm, and you can see the number. So I already put everything here. You don't really need to change these configurations. You have the frequency here, you have the length of the line. Let's see if I can make it a little larger. And you can have it a single phase view, or single line view, or 3 line view. We have it a single line view here. Again, you have another bus, and these are your loads. So you can use resistor, capacitor, and inductors as your loads, but then you have to give the numbers in ohm. And if you look at in power systems, we usually see our numbers, our loads as kilowatts. So we are going to use the other one, this one. So here, for example, this is per phase, and that's a very important fact. This is per phase. So if the manual that you have, the IEEE 37 bus system that you have says, for example, 1050 kilowatts, that's three phase, you have to break it in three single phase. Or if it gives you in three phase, then you're fine. So this is per phase, and we have it for one phase. So the R1 is the reactive power, and there is an important note here. If it's a positive number, it's an inductive load. It means if you want to apply a capacitor, you're going to use the same thing, no active power, but the reactive power is going to be negative, right? Positive means inductive, capacitor means negative. So you have to use the negative. This is rated load voltage, RMS, line to ground. These are very important. If you miss them, you're going to end up with wrong answers. No line to line. This is line to ground, the number that it wants here. And then again, this is the frequency. So I have it for all three phase. Again, this is a splitter. This is phase A. So this is B and this is C. So for some portions, you only have one load. So this is, for example, one load on phase C. Okay. Okay. I'm gonna upload some more files for you, but you can Google it anyway. So that's the entire network, 37 bus, and basically the point that you want to work on is this bus, 723. So this is kind of the 741 is the lowest voltage in the grid. So your goal would be to bring that up, but the description is in Canvas. Now, you also would need these files, IEEE 37 bus. So, here, you can see a lot of different feeders, test feeders, so you're gonna need the so this should give you the cable data, connector data. So I use a lot of these to create the file that you already saw, but you are gonna need, so this is the original paper that they talked about it and they presented it, so that's kind of the thing that you need. But I'll upload them later. So all the loads, all the lines, RX, everything is here. And I use this file to build that model. Now, the tricky part, again, running the simulation is very easy. So, to run a simulation, you just go here on top and there's a run button. And it starts running. That's the time of the simulation. That's percentage completed. If you go up here, these numbers are your real values, so they change a little bit over time, if you can see. And I also plotted some of them here for you to see. So that's the magnitude of VABC. This is your source, three-phase. Again, different values you can enter here. So that's the run, and your goal will be to monitor the voltage at the end, make sure it's acceptable. Right now, if the perfect voltage is 1 per unit or 1, you're getting 0.95, 0.95 here. So your goal is to bring that up a little bit with installing capacitor. So you're gonna need one of these, 3 of these with negative numbers. Once you have to do it trial and error, which means just put some numbers, run it until the numbers get high. The other part, which is the difficult part, is to calculate it, right? In reality, you can do trial and error. You have to go and calculate it. Now the tricky part is we usually use K-rise method, right? So how do you want to use K-rise? We calculate K-rise factor, but K-rise was for a single configuration, 1 ohm per mile impedance. If you look at this path, you have a lot of lines. Now the numbers here, 722, 723, these are the line configurations. So there are 3 or 4 different line configurations. So you're not using the same configuration everywhere in the network. So now your problem is when you start from the source, and that's where you have your substation. You have a 722, 2, but then you have 3, 3, 3, and I don't think you have any 4 on this path, but still. So, and then you have 721. So 3 different configuration, 3 different ohm per miles. In K-rise method, when you calculate I rise or delta V rise, you have to use real part of Z times I. Which Z you have to use now? So that's kind of the question. And I need you to come up with a good explanation of which method you want to use. Okay? You might need to do some approximations. Everything you do, you need to write the justification. Okay? So think about it. You want to use K-rise method? How do you want to do that? In your report, and that was a problem with a lot of reports for the first project, you didn't follow the format. So there was no introduction, no description of what you got, the results. So you need to follow the format. You lose points for that. A very nice looking report is required. You're going to lose format if your report is not good. But again, start working on it. The calculation is mainly offline, not in the PSCAD. Here you just put the numbers and then run it. So you don't really have that much to do with PSCAD. But it's a nice software to learn the basics of any day. Any question?
So we make our own configuration with the capacitors, and the values that we get to make it increase, we have to figure out or show by hand how those values were obtained.
Yes, so again, it has 2 parts. First is trial and error. So you install the capacitors, give it a number, run it, you see the voltage. It goes up a little bit. If it's enough, then you stop. If it's not enough, you increase the capacitors. You have 3 single phase, right? You run it again. So you run it until you get good voltages on 3 phases. So that will be the capacitors required to get the minimum voltage, minimum acceptable voltage there. But that's trial and error. The next part is using calculations to get the same value. You're not going to get exactly the same values, but it's going to be close enough. But you have to come up with a method. How do I get there? How do I calculate it using the K-rise method? So you're going to get the capacitance or the kilowatt for capacitors, and then again plug it in your simulation, run it again, and show that your voltages are actually going up with these numbers that you found. But again, you need a good justification for it. How did you come up with that specific number? You cannot just use your trial and error. I want calculation, math. And because the calculations are a lot, it's better to use MATLAB. It's a lot easier. So if you're using MATLAB, just append your codes, copy it and paste it at the end of the report as your appendix. This is the codes that I use from my MATLAB. If you're not using it, then that's fine. but again, there are a lot of complex numbers. I would definitely recommend using MATLAB. Questions? You good?